Okay, welcome everybody. Thank you for being here. And today we have with us Francesco Bonacci. He is now a postdoc. Oh, I'm sorry, I didn't change the presentation. I changed it on the website, so I should say young researcher.
Yeah.
So he's a young researcher. In the Italian system is a different system. So he's a young researcher at Università di Perugia, and he's working on contact aging in dense and attractive colloidal suspensions. So before you start talking about your work, can you give us a little insight about your academic path? Where did you study bachelor's, master's, and PhD, and exactly what are you doing now?
Yeah, sure. So first of all, I want to thank you for this very nice initiative and for the invitation. So I prepared some slides. Maybe I can
Great.
share the screen.
Yeah, go ahead.
So can you see the screen?
Yeah.
And please interrupt me if the microphone doesn't work or.
This is perfect now. Yeah.
Okay, so as you said, I'm a young researcher at the University of Perugia. So I put here a picture of the main square of Perugia. So it's a very nice city. It's probably not very famous abroad, but if you have time and you visit Italy and you are close to Rome or Florence, I suggest you to come. Just a few words.
Not many people know that in Perugia we have the biggest waterfalls in Europe.
Yeah.
Close to Perugia.
Very close to Perugia. Yeah, exactly. It's in my region. Actually, it's a very nice region to visit. So this is my journey so far in the educational and the research area. So Perugia is also the city where I got my master in physics in 2016. After that, I decided to go abroad to do my PhD. So yeah, I joined the Navier Lab in Paris. So Navier Lab is a mixed unity where there are physicists and engineers working together. It's in Marne-la-Vallée, close to Paris. And then I got my PhD degree in 2019, and I remained in France, in Paris, and I moved to do a postdoc of 3 years in SPCI, and I joined the PMMH lab, where they basically are interested in mechanics of heterogeneous material. And after these 3 years of postdoc, I got a position of young researcher in Perugia. So young researcher is like a postdoc, but I have also duty of teaching. And yeah, so it's 1 year that I have this position. And if I have a bit of time, I will explain what I'm currently doing in Perugia. So this is a small resume of the main topics I worked on during this period. As you can see, there are very different topics related always to mechanics, let me say, in the wide sense. So today I will talk mostly of rheology and mechanical aging of colloidal suspension. This is the work I've done in Navier during my PhD. And the other topics I show you are from the other position I during these years. In particular, I also worked on semi-flexible filaments in viscous flows using basically microfluidic tools. And then now in Perugia, I mostly work on the mechanical characterization of either nano or biomaterials using some light scattering techniques. And if you agree, and if you don't have any question, maybe I can start.
I just have a couple of very quick questions from a more practical point of view about your career, because I think that's always useful for very young people that might listen to us. How did you find your PhD and how did you find your postdocs? Like from a practical point of view, like really like.
Basically, thanks to networking. I mean, because I during my master stage intern, there was my supervisor that has spent some time in ESIA in Paris, which is an engineer school for electronic devices. And they looked for a candidate for a position on colloidal suspension. Then I applied and it worked. And then for me, it was a good time to go abroad because I was quite young. and I knew that for our career, it is very important to spend a bit of time abroad. So I took this opportunity and it worked well. And then for the postdoc, it's almost the same in the sense that my supervisor, Xavier Chateau, knew Anke Linden, which is a researcher working at PMH in SPCI. And so we start basically talking together, and I was really interested by changing a bit of topic of my research, and I was very interested by this fluid structure interaction problem between filaments and viscous flow. So I joined SPCI.
Great. Well,
And
that's all for me. Of course, if other people have questions, please just jump in. Otherwise, I guess you can start your presentation for today. And usually we allow people to ask questions during the presentation, but I let you choose what to do with them, of course. So I always suggest people raise your hand in with the button on Zoom. That's the best way to make yourself visible. And with that said, please go on.
So today I'm going to talk about my PhD project, which is about aging in dense and attractive colloidal suspension. As I said before, this work has been carried out at Navier Lab with Xavier Chateau, my supervisor, Julie Goyon, and Anaël Lemaitre. And this is also the result of a collaboration with Eric First from the University of Delaware. So I will try to convince you that physical contact between particles is very important in the rheology of colloidal suspension. Perhaps in the granular community, this was already known because there is a number of evidence that contact are very important in shaping the rheology of granular suspension. But maybe it was less obvious for colloidal suspension, where we have small particles, as you can see from this movie, which can move due to thermal fluctuation. So one may expect that in this condition, diffusion dominates the response of the suspension. Colloidal suspension are usually yield stress fluids. So these fluids can transition from liquid-like properties to solid-like properties, depending on the shear stress you impose on the system. So for example, if the stress is below the yield stress of the material, the system behaves as a solid. So it has a given elastic modulus, for example. And then if we increase the stress, we can move towards liquid-like behavior. So the system basically behaves like a liquid. And we can also, sorry, I have a question? No. Okay.
Yeah, I guess Abby has a question.
I had a very naive question. So if you're thinking about a solid, should not the viscosity be infinite?
Yeah, of course, this is just a picture to show a bit the change of the transition between two states. Of course, this is not actually a solid, it's a viscoelastic material. So the viscosity is not infinite, but at the end, the real part of the shear modulus is much higher than the other part, so the
Yeah,
imaginary part. And of course, we can also go from liquid-like to solid-like behavior if we now decrease the imposed stress. And this is true, of course, if we basically stop the shear. So in this case, we have before we have a liquid, and then the suspension goes toward a solid-like behavior. And this is basically what is basically aging. So aging is an evolution of the mechanical properties. So basically a strengthening of the suspension when we leave the suspension at rest. Why this is important? Well, this is important in many areas because we want to know how aging proceeds, because it's important for the stability of the suspension, but it's also important for the processing of, for example, of industrial suspension. Things, for example, in food and cosmetics area, where we need to know how the suspension change with the time of rest. So we usually don't want the system to change its mechanical properties with the time of rest. And other application can be found in the ink and paint industry, for example. So as I said before, we usually don't want aging because we want a system which is stable, but there are situations where actually aging is important, and we do want the material to recover solid-like properties rapidly. And this is, for example, the case of the cement paste, where basically when we handle this suspension, we usually want a low viscous material. Things, for example, if we want to spray the concrete on a wall, so we need a very low viscous material. But then, as soon as we stop the shear, the material should recover solid-like properties soon. So we want a very short settling time. And this is also important for avoid segregation of larger particle in the suspension or avoid failure of the structure. So what we can measure, how we can characterize the aging of the suspension? Well, we can measure basically two quantities. The first one is the elastic modulus, J prime, which gives us information on the elasticity of the suspension at rest. And then the other quantities is the yield stress, so which basically determine the minimum amount of stress we need to make the system flow. And as you can see, usually we observe a very strong increase of these two quantities with time. Well, what is the classical interpretation of aging? I think this picture from a very famous paper of Burns is quite instructive. So in this case, what we have on the left, you have basically a suspension where all the particles, due to aggregation, have formed a network which gives solid-like properties to the suspension. Then if we start shaking or shearing the suspension, we start breaking the bonds within the particles. And at the end, every particle is independent from the other. So in this case, we end up with a very unstructured sample, which has very low viscosity. Then what happens if we stop the shear? Things that we have Brownian particles, so they can move due to Brownian fluctuations. And so they basically start aggregating, and so they are able to reform the structure. So this is basically the classical interpretation of aging. Well, this has been demonstrated in a number of studies. Here I reported two examples. Especially this one is very beautiful from the Vermont group, where you can see that at time zero, each particle is basically independent. So there is no bonds between the particles, so every particle can move to the Brownian fluctuation. And then if we leave the system at rest, due to Brownian motion, particles can start to interact with each other, start to form bonds, and create these chains that eventually span the whole sample, so create this percolated network. And the system at the end behaves as a solid. But this type of experiment are basically limited to very, very specific samples. First of all, we know that most of people so far focused on transparent sample because they want to observe these particles on a microscope. But when you want a transparent system, meaning that you index match, you match the refractive index of particle and solution, you basically are killing van der Waals forces, which are strongly attractive. Next, these systems are usually in a low concentration regime, meaning that diffusion is important. So diffusion determines how much time it takes for one particle to see another particle, and so to form a bond. And usually people, what they have done is to sterically stabilize the particle using, for example, polymer grafted on the surface of the particle to avoid very strong bonds, so physical bonds. And to just induce a bit of attraction, what they do is to put polymer in the suspension, which basically induces depression forces. But depression forces are very low, so the strength of these forces is a few kBt. So Brownian diffusion can eventually open the bond between the particles. So we can form and break bonds. So the question we try to answer is that, okay, so we know that structural aging is at play in this kind of system, but does it is the case also when we have paste, so more concentrated system, and also turbid system. So as we have seen before, cement paste is turbid, so you don't have this index match. So what happens in this case? Well, the interaction with the particle is basically well described by Delvaux theory. So we have van der Waals attractive interaction, and then since we have ions in the suspension, we also have electrostatic repulsion. So our particles are charged, and so we have this kind of repulsion, double layer repulsion. Next, if we add salt to the system, which is, for example, the case in cement paste where there are a lot of ions, we are actually screening the particle charges, and thus we are weakening the repulsive coulombic forces. So if we reduce this repulsive interaction, we basically reduce this energy barrier at the point that we have only one minimum, which is which is when the particle come into contact. So if we add enough salt in the system, we can basically induce adhesion between the particle. So is structural aging, as we have seen in gels, in colloidal gels before, still at play in this kind of condition? So to answer this question, we designed a model system. We decided to use to study Stauber silica particles because basically it is quite easy to produce them in the lab with a very monodisperse size distribution. So we were able to produce particles with a range, diameter range between 500 and 2 microns, 500 nanometer and 2 microns. And then we add salt, we add calcium chloride to the suspension. We decided to use Stauber silica and calcium because we wanted to mimic basically cement paste. So we know that silica and calcium ions are very abundant in a cement paste. And then we increase the volume fraction above the gel point. So in the gel, we have a lower concentration, but we are still far from colloidal glasses. So we have in the range of 30–40% in volume fraction. And then we compute the DLVO potential between our particles. And then we realize that if we increase the salt concentration above 100 millimolar, we actually, the energy barrier avoiding adhesion between the particle was disappearing. Okay, so we start to do some rheology of the suspension. So we basically focused on the elastic modulus J prime and the yield stress over time. And we design a very very controlled protocol to erase the history of aging and then measuring the yield stress, for example, as a function of time. And these are typical results. So we can see that both J prime and the yield stress strongly increase with time of rest. And for example, we have almost a 6-fold increase in the elastic modulus and 2 times increase of the yield stress in almost 20 minutes. So our system, our suspension are aging. And then we try to visualize the suspension using a confocal microscope. So we slightly changed the composition of the suspension, adding a bit of glycerol to match a little bit the index of refraction in order to see the suspension using fluorescence. But we basically we were in the same, we didn't change the kinematic of aging of our suspension. And would like now to show you a movie on your left of a suspension at around 35% in volume fraction. This is the movie. So the movie is has a 10 minutes duration. And as you can see, there is nothing happening. So basically, all the particles that we can imagine remain in the same position. So we were quite surprised to observe this kind of behavior. And if you want to be more quantitative, we can basically reconstruct the position of the particle. We can track the position of the particle, for example, at different times during aging. And as you can see, basically all the particle, the microstructure is frozen. You can probably see some particles appear and disappear, but this was only an effect of photobleaching of the dye. So we basically we lose some particle with the tracking algorithm. And we can confirm this observation, for example, computing some structural property of the suspension, such as the pair distribution function. So the main conclusion of this was that in our condition of turbidity and salinity, we basically see that aging proceeds in the absence of structural evolution, in contrast with what we have observed, for example, in gels. So, of course, there is a different mechanism at play. And to understand what was going on at the interface between our particle, where probably aging is proceeding, we decided to use laser tweezers. So I spent a bit of time in US in the Eric First laboratory to perform some kind of experiment with optical tweezer. So optical tweezer basically is an optic technique where we have a laser, a very focused laser, and a particle which is close to the focus of the laser basically is trapped in the focus. And if it moves a little bit from the center of the focus, it experiences a restoring force, which is basically proportional to the displacement. So this trap, this optical trap, basically act as a spring. So with this kind of system, we can apply and measure very small forces in the range of piconewtons. So the first experiment we tried is an approach retraction experiment. So we trap two particles and we approach the particle, and then we apply a force, attraction force. And the idea was, of course, to change the time of contact between the particle and see what was the force needed to open the bond. So now I have two movies. The first one is for a very low salt concentration on your left, and on your right we have a larger salt concentration where we start observing in the suspension yield stress and edging effect. So as you can see from the left, we were always able to open the bond, meaning that basically the bond is not very strong. While on your right, where we start observing edging effect on the suspension, we can clearly see that we were not able to open the contact. So we started increasing the laser power to increase the stiffness of the traps, try to applying larger forces, and we didn't manage to open the contact in any condition. And so we started thinking, okay, let us try to calculate what will be the yield stress of the elastic modulus of the suspension in this condition if the bonds open by traction forces. And we realized that the value we obtained were very much larger than what we observed by rheometry. So if the bonds open, they will probably open not by traction forces, but by bending moments. So we decided to use a different type of experiment, and we use this 3-point bending test designed by Pantin and First in 2006, where they were able to assembly rod of particles using the traps. And then once the rod is formed, you basically use only three traps. Two at the ends of the rod are held fixed, while we start moving the center trap perpendicularly to the rod. So basically we are applying a bending moment. And since we can track the position of the particle, we can basically compute the deformation and the force on the rod. So the deformation is basically delta, which is the deflection of the rod. And the force can be computed by looking at the position of the end particle with respect to the position at rest. So we can measure forces, we can measure deflection, and so we can basically plot the force against the deflection. And these are typical data we get. So as you can see, for small forces at the beginning, we have a linear relationship, which is basically an elastic response. We also observe that this is reversible, so it's really an elastic response. And this is characterized by bending stiffness of the rod, which is basically the slope of the curve. And then at some point, when the bending moment or the bending force is larger than a given threshold, we start observing some rearrangement, some rupture of the rod, as you can see from this sudden increase of the deformation and decrease of the force. So for the first regime, where we have a linear elastic response, we observe the shape of the rod during bending. And as you can see from the figure on the left, the shape of the rod is well described by the Euler-Bernoulli beam theory, meaning that basically our particle rod behaves as a beam, as a classical beam. So we can fit our data using this model. And so we can retrieve the bending stiffness. We can measure the bending stiffness, can relate this bending stiffness to the flexural modulus of the beam and the length of the rod. And then since we have not a continuous beam, but we have a chain of particles, we also model the system using basically rigid particles connected by a rolling spring of stiffness Kr. And using these two models, basically we can we can measure actually the rolling stiffness between two particles, Kr. And this is basically related to Kb, so the slope of the force deflection curve, the length of the rod, the radius of the particle, and a numerical factor. So with this kind of experiment, we can actually measure the rolling stiffness between two contacts, between two particles. Note that the LVO theory cannot account for a rolling stiffness because it's a centrosymmetric potential. So this means, since we have a resistance to rolling, it means that particles are forming a physical contact, so are in addition. Then what we can do to study aging, well, we assemble a rod, we perform a bending experiment, then we wait some time, then we perform again a bending experiment, and so on. So we basically are measuring the bending stiffness as a function of the aging time. And this is a typical result, very, very nice result we get. So we can see that the slope of this curve increases with time, with the time of rest. And this means basically that our rod are aging. And we can, from our model, measure the bending rigidity, the rolling rigidity between two particles. And this is these are the results we get. So we can see that Kr strongly increases with time. Also, of course, we use different number of particles in the rod. Kr should be independent of the number of particles in the rod because it's a property of the contact. And we also changed the ionic strength, but we didn't observe any huge difference between ionic strength above 100 millimolars. Then, okay, we know that now the contacts are aging, and can we relate this contact aging to the aging of the suspensions? So we start observing from the macroscopic data, so the G prime, because we are talking about elastic behavior. So we took the G prime data, and then we compare to the rolling stiffness data. And you can see that we have very similar behavior, very similar characteristic times. And we can actually show that if we plot one against the other, basically we get a very beautiful linear relationship, meaning that actually the aging of the shear modulus is solely determined by the aging of our contacts, so of the aging of Kr. And so we model the shear modulus using this linear relationship, where S here is a time-independent structure factor, which basically depends on the volume fraction of the suspension, so the number of contacts in the suspension. So with this kind of experiment, we actually demonstrated that aging is not due to the change in S, so a change in the number of bonds or change in the structure of the suspension, but is only due to change in the contact behavior, in the stiffness of the contact. Then we also had this very nice data above a critical rolling threshold. And we tried to relate this behavior to the other properties of our suspension, that is the yield stress. So we start looking at the shape of the rod just before and after the yielding event. And as you can see here, so we have in blue we see that the shape is well described by this Euler-Bernoulli beam theory. And just after this yielding event, we can clearly identify the bond which has undergone a yielding, a rearrangement. So from the measure of the critical force and the position of this bond, we actually can compute the critical bending moment, which must be overcome to see a rearrangement in the rod. And we start measuring this critical moment as a function of time, as we have done for the KR. And these are the results. So again, we see that this critical moment increases with time. And this is almost independent of the ionic strength above this value. So this is another manifestation of the aging of our contact. And can we relate the increase of the critical moment, which I recall is related to the yielding of the rod, to the yield stress of the suspensions? So again, we start from the macroscopic data and the microscopic data. We plot one close to the other, and we can clearly observe that they have very similar behavior again. And indeed, what we can do is that we can reconstruct the yield stress of the suspension using our microscopic data. And again, we can see that this is an error. It should be, no, yeah, okay. It's okay. So we can see that the yield stress of the suspension is basically related to the aging of the yield stress is related to the aging of the critical moment. And again, this Q is a time-independent structure factor, which is not the same as for the shear modulus, because yielding can occur in a different way with respect to the elasticity of the suspension, but still is a quantity that is independent of time, and it depends only on the number of contacts involved in the yielding event. So at the end, we demonstrated that aging is in our suspension is only due to contact aging, and now we try to be more quantitative. This is probably the most technical part of this talk. We started with the elastic behavior. So we know that the rolling stiffness within the particles is related to the size of the typical size of the contact. So this AC. And this AC can be related to the adhesion between the particles. So we use standard adhesion theories, such as the GKR adhesion theory, which gives us an expression for the contact radius AC as a function of the size of the particle, the elastic properties of the particle, and WV, which is the adhesion energy. So since the elastic properties and the size do not change with time, the only possibility for contact aging is an increase of the adhesion energy within the particle. So we basically have an expression for Kr as a function of the adhesion energy. And one possible mechanism that we suppose at play is this one. So we know that silica particle can basically form these siloxane complexes by removing a water molecule. So we have this silanol group at the surface of the particle. With time, this silanol group can basically react and form an AC-OIC bond, which is much stronger than this bond. So this could be a process at play which can explain the increase of the adhesion energy with time. Next, we also know that at some point, these bonds start rolling. The particles start rolling above the other particle, and we spend a bit of time trying to understand what's going on. And at the end, we found this very beautiful paper from Critch, where they basically compute, they treat the problem using fracture mechanics. So during the rolling, basically we have a closing fracture, for example, here on the right, and an opening fracture on the left. And this, of course, the surface energy for opening and closing are not the same, and this is known. So there is a so-called adhesion hysteresis, W. And in this paper, they basically related the critical angle before rolling to this adhesion hysteresis. And in our case, we can show that this critical angle is basically proportional, inversely proportional to the square root of the Kr, of the rolling stiffness. And also we know that this critical angle is related to the critical bending moment. So combining these two, we actually should have in our data a microscopic constitutive equation related to the critical bending moment, MC, to the rolling stiffness, where G is only dependent on the adhesion hysteresis and on the elastic properties of the particle. So we verified this fact, this relation, and by plotting MC against Kr, and indeed what we show here is that we have this very beautiful relationship. So we have in a log-log plot this 1/2 slope. So using this, we were also able to compute the adhesion hysteresis between our particles. So now, since we know that the Kr is related to the shear modulus of the suspension, we know that MC, the critical moment, is related to the yield stress of the suspension. And since we know that MC and Kr are related, we do expect that we have the same constitutive equation or relationship in our macroscopic data, in our suspension. And indeed, this is the case. And we can clearly show that the yield stress is proportional actually to the shear modulus of the suspension, where this prefactor is basically only dependent on the characteristic of the contact. So we have the Young modulus, the Poisson ratio, and the adhesion hysteresis. So we can show it by plotting the yield stress as a function of G prime over A, the radius of the particle. And for different ionic strength, different particle size, different concentration, we can see that we have this beautiful collapse of the data. So this is very important, I think, because we have not only shown that contact aging determine the suspension aging, but also these two quantities are related, so that, for example, it is possible to measure the yield stress by knowing the shear modulus of the suspension. And you know, measuring the shear modulus is less invasive than measuring the yield stress, because in the shear modulus measurement, you basically probe the suspension in its elastic regime. So you are not changing the macrostructure of the suspension. While the yield stress, you have to break the bonds. So you have to it's a more invasive technique. And also this gives us an idea how to change, for example, the yield stress, changing the contact properties of the particle. So this is my take-home message, that contacts drive mechanical aging in the adhesive and dense suspension. With dense is not close to the colloidal glasses, but in a regime of close to pasties. So I don't know if there are any questions.
Well, thank you, Francesco. That was great. That was really, really great. Well, Jeff Morris is also thanking you, saying very nice work and a really clear presentation of the mechanics, and I do agree. Abby is also saying thank you, and that's true. That was very clear, and that was a very, very cool work. I'm happy to see. I mean, I've seen this part of this work now, well, like 4 years ago and 3 years ago. I'm happy to see that went a long way beyond what you showed some years ago. This is great. Questions? Yeah. So questions now. Yeah. Abby's saying outstanding work. I mean, I'm just reading the chat. Probably you can also see that, but it's nice to read it.
I got a question, Francesco. This was really cool. These are things we are just beginning to think about from a simulation perspective. So seeing experiments is really encouraging. I had a few maybe stupid questions. So when you think about the addition energy, and I can imagine that, why would it not be time dependent?
The addition energy in the particles.
Yes. Like if you go like a few slides back.
Yeah.
Yeah, or maybe even like 2 slides further. That was a great slide. One more.
This one.
Like your second to last slide, where you had the relation between yeah. So what I'm thinking about is, so you try to relate yield stress, time dependence of yield stress, and the time dependence of G prime. I'm curious about why would delta W or not have a time dependence as well.
Yeah, it's a very good point indeed. So we think that this delta W is not changing over time because basically if you look at the contact, as there are formation of these siloxane complexes, this will happen in the center of the contact. So this will increase the addition energy, so the particle will start to form a larger neck, but the periphery of the contact is not aging as the center of the contact. So the periphery of the contact is fleshly formed. So that's why we think that probably this is why the addition hysteresis is not changing over time. I'm not sure it was clear. So the fact that if you increase the addition energy, you form a new contact on the periphery of the contact, but this is new, so it's not aging.
Are you not increasing the area of contact during aging?
Yes, so the AC is around 10 nanometers and increasing up to 15 or 20 nanometers, something like that. So at least this is our interpretation, why there is no clear evidence of W changing over time.
Because I mean, what I was thinking is, if you're increasing the area of contact, I mean, in some sense, the pull-off force would change because the pull-off force depends on the area of the contact.
Yeah, sure.
But you're not changing the area of the contact in this formula, right? Here A is constant. That's what you were saying. Like if the area was changing, the neck would increase, but that would be a new contact. So in that case, W would change.
No, it's not like this. I mean, what we think is that W is increasing, so this will actually increase the contact area. So there is an increase of AC, and this is why KR is increasing, because AC is increasing.
Yeah.
But then when you increase AC, you increase in the periphery of the contact, where basically this is a new contact, so it's not there is no formation of these bridges. So this
W has a function. is a function of t, but the change in the W is not a function of t. Is that what you're suggesting?
No. The change of W is a function of time, because you replace this hydrogen bond with a covalent bond.
Yeah.
Okay.
So when you go to your last slide, when you try to relate the two things, then you take the delta W not being a function of time. That is just the point that I'm confused.
Yeah. So W is changing with time and not W. So basically, W is different from the adhesion energy. It's the adhesion hysteresis.
Okay.
So W is increasing over time, but not the hysteresis.
Okay.
And this is because the energy you need to close and open the contact is in the periphery of the contact, where aging is not at play yet. It's mostly at play in the center of the contact.
Okay.
Even though you form a new contact at the trailing and opening edge, this is a new contact, so it's not aged yet. That's why the adhesion hysteresis is not changing so much.
Interesting.
Interesting.
This is our interpretation.
I mean, it makes sense, but
yeah, I need to revisit my PhD thesis. That was exactly about it. No, this makes sense. This makes sense. This makes sense. So do you also observe some hysteresis in your rheology, like if you do the forward and the backward ramp?
We didn't try in details, so we tried a few times, but it was not very simple to make this measurement. So we actually don't have an answer, but I think it could be very nice to relate the hysteresis with this back and forth.
Hysteresis of the contact, right?
Yeah.
Thanks so much. This was really cool.
You're welcome.
it was indeed very cool. Other questions? So this was work with colloidal suspensions, everything. I mean, I guess this can apply to any suspension, right?
Yeah, but then if you increase the size of the particles, probably adhesion is start to be less important.
Depends. I mean, I'm thinking from a numerical point of view, so I can play around as much as I want. Okay.
And just a suggestion, like, have you looked at the work by Wilson Poon?
Yeah.
So he has done some work on like how to relate basically some of like not the time dependence, but thinking about constraints that would offer that the adhesion would offer in terms of rolling and other things, and relate that to rheology. Not directly related, but worth maybe having a look. So I just had one more quick question. So when you have adhesion, why are you putting all the adhesion only into rolling? So when you have adhesion and you're thinking about these siloxane complexes, would not they affect the torsion as well?
Should also observe this aging in the
So adhesion is, so rolling is like what you are thinking about this, but torsion would be something like this.
Yeah. Torsion. Yeah, of course, but we cannot measure this. I mean, I think with at least with optical tweezers, we couldn't measure it, and I don't know if it's. Of course, this will have an influence on the rheology, but we cannot actually quantify the importance of torsion. We know that traction is not the way the suspension yield, because it's the force we need to open the contact using traction is very large. That cannot be And we know that, of course, bending is much more complex.
Yep. Yeah.
We don't know about torsion.
So I had a paper back in 2020 where we tried to think about hydrogen bonding in terms of rolling resistance. And we thought that the hydrogen bonding is leading to some adhesion, and adhesion is leading to rolling resistance between particles.
Okay.
So, I mean, this is an interpretation we have because it's known. This
I
process
really like it. I really like it.
It's really known, but of course, we know that the LVO theory is not working. We know that there are a lot of problems when you confine ions. You have structuring of water in the contact, so we have a lot of process that we cannot actually access. It's difficult to say what is the aging process at play. We think that this could be a good candidate.
Yeah. So I'll just drop it in the chat. I mean, if you want to have a look later on. But thank you so much. This was incredible. Thank you.
Okay. Well, I thank you again, and I'm going to stop the recording here.